I'd like to introduce our next presenter, Mohamed Hafez from the University of California, Davis, and he will be giving a talk titled Numerical Solutions of Nonlinear Differential Equations for STEM College Education. So I will hand it off to him now, and thank you all for being here.
Hi, everybody. This is a picture of me because the camera is not easy to change the setting. And this is the title of my talk, Numerical Solutions of Nonlinear Differential Equation for STEM College Education. And these are the names of the students I work with them. And the first one is Faiza Alvi. She was a senior undergraduate student last year when she did that. Now she graduated and she works as an engineer in a space company in the Bay Area. Second one is Naijing Goa. She also was a senior undergraduate student and she graduated in June and she's now a graduate student at Stanford. And the third one is Yash Danahi, and he also graduated. He was senior undergraduate student, and he's now a graduate student at Stanford. I was lucky to work with these excellent students, and we have a system at UC Davis that students can sign for research units. And these research units, they are open and they have choice of what they do. And I found this a very good mechanism, especially for excellent students. They do it because they like to do it. There is no obligation. I announce for that in my classes, and I usually have 2 or 3 students every quarter. And so far, I was very happy to work with the students. They are self-motivated, excellent students, and they challenge you, actually. So I like to go through the process I do for the numerical simulations. This is the contents of my talk. Basically, I will give an introduction and then I will have students' projects. I'll show you their results. And some of this are based on the courses we teach in my department, mechanical and aerospace engineering. And we have basically some projects on heat transfer, fluid mechanics, and dynamics and oscillations, and instruction mechanics. And the emphasis in all these projects is nonlinearity. How do we deal with nonlinearity? And I will go through that and by examples. So there is no general theory for nonlinear problems, but of course we have most of the nonlinear problems we have to solve it by computers, and we have Newton's method and fixed point iterations and things like that. But every problem has its challenges, and I will go through that. And then I have some conclusions if there is time to discuss that. Now, the numerical process, the numerical simulation process have 5 steps. We have the physical problem, then we have the mathematical formulation, then we have numerical methods, and programming and data analysis. I will talk about the first 3. Programming, we use MATLAB usually at UC Davis, and there are issues for computer scientists like parallel computing, GPU, and data analysis. We just use plotting and animation, but there are issues like data mining, data compression. This is not covered here. I mean, so we have minimum skills of programming and simple tools for plotting. And these projects are collected from the work of the students. And I was lucky to, over the years, to have these interactions with the students. And I co-authored the book with my former PhD students, William Tavernetti, and it was published a couple of years ago. And the book is talking about computer simulations for integrated STEM college education. And I want to emphasize here this business of STEM. I mean, we have courses in science and in engineering and in mathematics. And the idea of integrated STEM is after the students learn these subjects, I want to do independent research for some of the problems common in this STEM education, using computers, of course. And you will see how they put computers to use to get solutions for problems they have seen in these courses. So here we use mathematics and numerics as tools to understand the physical problem, and to produce results for some interesting problems. So we'll start with the physical problems. So I confine myself to engineering mechanics, and we have dynamics, of course, and we have solid mechanics, we have fluid mechanics, and we'll talk about some of these problems from these courses. Then we have heat transfer, and we have chemical reactions and combustion. And we'll not talk about combustion and chemical reactions in this lecture. And the book has covered some of these topics, and I can refer to the book. And here is the book, actually. This is the book, Introduction to Computer Simulation for Integrated STEM Education, by myself and Tavernetti. It was published by World Scientific in 2019. And these are some of the examples. I mean, motion of the airplane and rocket launching the orbital mechanics, the fluid mechanics, flow in a pipe, and shock waves. This is, I mean, tension, bending, and so. And there are some mathematics also about mass spring system. And this is this is non-homogeneous solutions when you load the system. This is resonance. This is interesting problems with bifurcation and fractals and things like that. So the book is not a textbook. The book is to accompany a textbook, and it's self-contained. The students can read the book and learn from the book without any need for instructions. So this is what, for example, in dynamics, I will talk about two-body problems. And this is an outgrowth. It's nonlinear equations because now we use the gravitational law rather than constant acceleration and trajectory. And we have also spin stabilization. And the interesting part is to see if the numerics will honor the integration, the integral invariance. There's integral of motions like energy and momentum, angular momentum. And we do, if we use the right schemes, we do. In fluid mechanics, I picked up problems related to boundary layers and related to compressible flow in nozzles with and without shocks. In solid mechanics, I picked up problems from, of course, fluid mechanics, the bound layer is nonlinear and the compressible flow is nonlinear and essential. Nonlinearity is essential there. In solid mechanics, I have in the book the linear part of tension in the cable and the bending of a beam and buckling of a column. And I extend that in this talk for nonlinear problems of tension with large deflection, bending with large deflection, and buckling, nonlinear buckling. For heat transfer, in the book, there is Newton cooling law. We've seen that in the conference by many speakers. I add to that the nonlinear, radiation problem. And it's transient, so you solve ordinary differential equation and you can relate that as Newton's cooling law with variable coefficients, the coefficients function of temperature. And this is the physical problem. The mathematics involved, of course, we have basic mathematics, calculus, and geometry, and algebra. And that's basically high school. And the geometry, we use conic sections. And for algebra, we use elementary functions and polynomial equations. And calculus, the integration and differentiation, fundamental theorem of calculus. And in numerical methods, here, this is the college mathematics. We have linear algebra, Gaussian elimination, and eigenvalue problem. And In ordinary differential equation, we have initial value problem, first order and second order equation, boundary value problem, second order and fourth order equation, and eigenvalue problems for both. In numerical methods, we have numerical approximations of functions and derivatives and integrals, numerical linear algebra, and numerical ordinary differential equations. So these students have went through all of that, and especially they consider these math tools useful, but we want to show how to use these math tools to solve the physical problems we mentioned before, whether it is heat transfer or fluid or dynamics or solid mechanics. So that is the physical problem and the mathematical formulation. So the numerical methods are standard, simple numerical methods. So we have discretization of the domain, finite uniform mesh, and then discretization of the equation, finite difference, first derivative, central difference, backward difference, forward difference, second derivatives, third derivatives, fourth derivatives. And then for solution of initial value problem, we have explicit method, implicit method. For boundary value problem, we have iterative methods and direct methods. And we use tridiagonal solver and pentadiagonal solver for the biharmonic equation. So for initial value problem, we have this also improved Euler, and improved Euler, which is Runge-Kutta 2, or predictor corrector, a second order 3-level scheme. A very standard method. And now we have the treatment of initial conditions. We have, if we have second order scheme, we use Taylor-C expansion for the second point. If we have boundary value problem, we have a fictitious point to implement the equations. We touch on the stability of simple schemes, like there is a restriction on delta T for first order equation and for second order explicit method. So now I want to show you some results from the students. We start with Blasius equation. Blasius equation is nonlinear equation. And we write it, in fact, as a second order. This is third order equation. And you can use shooting method to do that by writing as system of 3 first order equations. Or you can do it as a second order equation and use tridiagonal equation to solve this coupled by iterating on the coefficient. There is another one. This is across the bound layer. There is another differential equation very useful for flow with pressure gradient. That's for Korman integral equation, and you have to solve an ordinary differential equation with the flow. And Bolhausen has a very famous Runge-Kutta method solutions for this without separation. And these are the solutions from FISA for the Blasius equation, the solution of the velocity and the stream function. And for compressible flow, we have 3 cases: flow without shocks, flow with shock fitting, and flow with shock capturing. And this is the solution, actually. This is the equations. This is the area distribution of the nozzle. And this is the governing equation. It's nonlinear governing equation. And to start the calculation, we have to use L'Hopital rule, because if you want to calculate the Mach number distribution versus the area, you have to divide by that. And when at the throat, that's 0. So you have, this is the first stumbling block. You have to go through the first point, and you use orbital rule to get the slope. Once you do that, you go this. And step by step, that's the design condition, and you get supersonic flow from the throw. But if you have a shock, then you have to solve this problem. And it becomes 2-point boundary value problem because you have to meet the end condition. But this first order equation, but because it's nonlinear, we can do the problem because we have to augment this with conservation laws. Across the shock, there is a law conserving mass, momentum, and energy. And this is the solution, and actually compares well with the classical solution published by Professor Chateau in his book. So that is FISA. As far as Neijing did nonlinear oscillations, nonlinear pendulum, and she get this solution. And she did also Duffin equation, nonlinear stiffness, and she got a solution. And also van der Waals equation, that is nonlinear damping. And in order to do the nonlinear damping, you have to have two-step method because you don't want to linearize them. You just, this is.
That one's sideways.
Pardon me?
I thought that slide was sideways, but now you're on the slide.
Okay. And this is interesting results from Rayleigh equation. And all of these are very specialized topics, but she was able to do that with very simple standard method. The second problem was a two-body problem, and this is the energy conservation, beautiful, and this is the momentum conservation. The third problem was the spinning stabilization. We have three equations non-linearly coupled, and she got a solution, no problem. This is the kinetic energy and the angular momentum. They are conserved, and these are the integrals of motion. This is the angular momentum, and this is the energy. So the scheme works, very simple scheme, central difference, and works. And then I want to conclude with the work of Yash. Yash did structures, building, buckling, and using shooting method, actually. So he used a nonlinear buckling and nonlinear bending and nonlinear tension, and he did both finite difference methods with boundary value, 2-point boundary value problem, as well as the shooting method. The shooting method is very useful to avoid problems. This is the tension problem, this is the linear, and this is the nonlinear problems. This has been shown in the conference, and this is the solution. And the bending, again, this is the linear problem, and then he has the nonlinear problem where you use the full formula for the curvature. And this is the solutions. Okay, and this also, this is the buckling, this is the buckling, this is the bending. But he has also the buckling, this is the buckling. This lambda is the eigenvalue. So these students, they did a good job in my mind, and they learned something. And the conclusion I want to make is that just teaching them tools in mathematics and talk about the problems in the classes for engineering, physics, and there is something missing. I mean, I want them to use the tools they learn in mathematics, and assuming that they know how to use computers and they have required courses in programming, I want to combine these three things. I want to combine the computer programming and the the physics and the science. They learned about vibration, about fluids, about, and the mathematics and the numerics. They as how to integrate differential equation, how to get solutions, and with simple minded, very standard, no sophistication in this. I mean, once you learn the tool, you can put it to work. Of course, there are certain problems you need specialists. We never talk about elliptic function. We talk about elementary functions, sine and cosine and exponential and things like that. So, and I have been doing that for some years now. And the book is actually the result of all these efforts. And when my co-author, he was my former graduate student, he's now a lecturer, and I decided to continue this with the new students. So I want to show you what they did last year. Thank you very much.
I have a quick question.
Sure.
These were all undergraduate students?
Yes, senior undergraduate students after they finished all the required courses of engineering and mathematics and computer. And they like to have research units. Research units is a very nice mechanism. Students can sign for 1 or 2 units research. It's like senior design courses, but it is not required.
Right.
And the students choose the professor as well as it was meant to satisfy the unit requirements, but actually these good students, they pass these requirements. The requirements is 180 units. They have 220 units. Still, because they took my classes and I announced that they can have research units, they signed for these research units, and we meet once or twice a week for an hour or two, and they write a report and make a presentation at the end of the quarter. I collected all of this over the years, and I was lucky to have Tavarnetti to help me with the book. But after he left, I said, okay, I might as well write a paper about this and show their work.
Thank you. Excellent.
Thank you.
Mohamed, this is a very good starting point. This is the senior students, am I right?
Yes. I have also junior students, but they must have the required courses. I don't want to teach them the stuff they learn in math, like the rule, Simpson's rule. I don't teach them that. And Runge-Kutta method, Gaussian elimination, they know that already. And then they know boundary layer, they know shock waves, and they know buckling, bending. But now the question is how to put this together to produce results.
I thought mechanical engineering and chemical engineering, I used to teach this as a course, numerical solution of nonlinear differential and partial differential equation, the same location, same place in Boehner Hall.
Yes. So, I remember the name of the professor, Subhash. Professor Subhash, you know him?
Yeah.
Previous
to that one, I used to teach in the chemical engineering. We used to have everybody from engineering lined up. We used to have around 20, 25 students. I'm surprised that
we have a course. I teach a course in engineering analysis. which
Okay.
that is different. That is a one-to-one. I mean, I have the students. This is
Okay.
one-to-one, a students and a professor, and the students choose the professor and choose the topic, and the professor formulate a project, and
Okay.
we work together to get the results, and the students present this at the end of the quarter. This is not a course with 20 students. No.
Ah, okay.
No.
Okay.
One-to-one.
Okay. Good job. Good job. It's definitely needed for, not only, in engineering, any application side, some of these applications are very.
Yeah, and also I enjoyed the students because they usually are excellent students. And some of them, I told you, the two of them went to Stanford. I have students went to Caltech. I have students went to MIT. And they also appreciate this because it gives them experience to put the stuff together and see the power of computers and numerical methods and the synergetic effect when you have the theory and the numerics. We have also added experiments, but that was another talk, how to compare the results with experiments.
Okay, great. Excellent. Excellent.
Thank you. If you come to Davis, let me know, please.
Yeah, I will definitely. That's I was there,
Dinner hall, second floor. Just ask for Hafez.
Yeah, we were on the third floor, I think so. Yeah.
Yes. Thank you. Thank you for listening.
Yeah, thank you. Very good.
Thank you.
Yes, thank you so much for that talk, Mohamed, and thank you all for your questions.